All right, so now on this problem, the first part of this problem is simply Hooke's law. If I look at the forces that are acting on the object, because if you read the question, it says here that a mass of 2 kilograms is hung on a spring so that the mass hangs at rest. So it's not moving up or down, it's just hanging. So if it's hanging, then that means the forces that are acting on here have to be balanced. And the only forces that are going to be acting on this are going to be the spring force in that direction and the weight in that direction. So you've got the spring force up, and it's going to be balanced by the weight of the mass. So the formula for the spring equals minus k. Well, actually, I don't have to put the minus. The minus just tells me it's in the opposite direction to the direction it's being displaced. So what I mean by that is if you look at the picture, if this thing is lower than where it would be without the weight on it, then the spring force is always going to be in an opposite direction to the direction it's being displaced. Okay, and it's being displaced below, so below where it would be without the weight on it, so the spring force is up. So the minus, that's all that means. So if I want to write an equation that's going to help me solve this, I just have to say that the spring force, so again, the formula is minus kx, but I can write it as kx there. And the weight equals mg. So I know that they have to be equal if it's just hanging at rest. So kx equals mg. And if I want to, it says how much is the spring stretched? That's the x. That's how much it's being stretched. So if I solve for x, it's just going to be mg divided by k. And if we put in the numbers, so the mass is 2 kilograms. G is, again, you could use 9.8 or 10. I said you could use 10 for this. And then you're dividing that by 30 newtons per meter. Right? And if you solve that with the numbers that I gave, it came out to be 0.653 meters. And that's it. That's the problem. So you're setting the spring force, and that's Hooke's law. Remember, Hooke's law says that F equals minus Kx. So that's what you're using here to solve this problem. Now in part B, in problem 3, it says if we pull the mass in number 2 down further and release it from rest, what's the angular frequency? Well, look, we have K in the problem above, and we have M. And those are the only 2 variables. So it's not even like I have to do a complicated thing. I just have to pick the equation and substitute. So if I'm solving for the angular frequency, the formula is the square root of K over M. And I know both of those numbers. So the square root of K is 30 newtons per meter. And the M is 2 kilograms. And if I solve that, my units will come out in radians per second, because angular frequency is going to be, and now don't confuse omega with frequency, okay? Because with like the frequency this. We've got frequency, which is 1 over the period, but then we have the angular frequency, omega. And the units for omega, the units for this would be seconds to the -1 or hertz. Okay, so if that's in seconds, then this is seconds to the -1, which is hertz. But the units for this are radians per second. And if you solve it, that's like the square root of 15. And that comes out to be, I got 3.87 radians per second.